Let's start.
Hello everybody, I'm Dr. Vaishali Kerekatte, a scientist in Dr. Sanjeeva Srivastava's lab at IIT Bombay in Mumbai. I'm also a teaching assistant for his NPTEL MOOC course on Interactomics. So today we are in the 7th week of our 8-week MOOC course. One on Introduction to Proteomics and the other is the Interactomics course, both of which are conducted by Dr. Srivastava. Today's live demo is on SPR data analysis, where those of you who are registered for the course have been sent the BR evaluation software so that you can have some hands-on experience in the data analysis. For those who have not registered, you can, but who are interested, please do send us an email and we will be happy to arrange some hands-on analysis later on. For those of you who are joining us live and those who will watch later, we hope this small hands-on session will get you interested in using SPR for your experiments. So before we start with the data analysis, let me give you a short introduction on SPR to brush up on the basics of SPR. So we'll go over to the PowerPoint presentation. So surface plasmon resonance, or SPR, is a method which allows real-time, label-free detection of biomolecular interactions. SPR helps you to study protein-protein interactions, protein nucleic acid interactions, protein small molecule interactions, antibody protein interactions, as well as protein lipid interactions. This is a very simple schematic of what SPR is about. So in SPR, what happens is you have a sensor chip, which is typically has a gold film on it. The incident light is focused from a light source. This is polarized light, which falls on your sensor chip, and it is reflected off this surface, and there is a detection unit which detects any change in refractive index. So SPR basically measures the change in refractive index. Now what happens is on the other side of your sensor chip, you can immobilize any protein or any biomolecule that you want to study, and then you have an aqueous medium through which your analyte that you're testing the binding to the ligand is flown. So if you see here, this is the flow channel. Your analyte is flowing through it, and if there is any binding, it will bind to the ligand, and then it flows out. And any change in refractive index will be measured. There are basically three major steps in an SPR assay. One is the immobilization, where you attach your ligand to your sensor chip surface. There are two kinds of immobilization techniques. You can have a direct technique or a capture technique. And we won't go much into detail in this session. If you're interested in learning more about this, you can attend our Interactomics MOOC course, where all these terms and the experiment's details have been explained. Then the second step is the sample injection or the interaction phase, where your analyte in running buffer flows over your ligand immobilized on sensor and binds to it. And the output from this is a sensorgram. And this sensorgram is what we are going to analyze today. And the last step is regeneration, where after the binding is over, you want to remove all bound analytes from the ligand so as to prepare your chip, to prepare the surface for the next round of analyte binding. So this is a sensorgram. It is nothing but when you plot response units versus time. And if you look at this sensorgram here, what is happening is, in the beginning you are flowing your only your running buffer over a chip where the ligand has already been immobilized. So you get a baseline curve over here. This is the baseline. Then Then you start flowing your sample in the running buffer. You start flowing your sample over the in running buffer over your chip. And as you can see here, there is an association. This is where the binding is occurring. Then you, at a defined time, which is typically in seconds, it could be 30 seconds, 60, 300, depending on what your optimization has been has shown. You withdraw the sample from your running buffer. So here you no longer have your analyte in the running buffer. So you have the dissociation phase where your analyte is dissociating from the ligand. And then you, at the end of that, you start with you flow the regeneration solution where you're again preparing your chip surface for a fresh round of binding. And then again flow the sample buffer. So this is a very typical textbook picture of a sensorgram. And usually the shape of the curve reveals the kinetics of your interaction. If you have a steep association curve, then it is a fast on rate. If it is, if it is a slow dissociator, then it shows as a slow dissociation on your sensorgram. So the shape of the curve is very important for determining what kind of binding is taking place. And the output from this is SPR experiments can give you information on whether it is binding at all, a yes-no binding, how specific is the binding, how strong is it, how fast is it, and how much. So in our kinetics experiment today, we are going to mostly see how fast is the binding, and that will be revealed from your on rate and off rate constants, the Ka and the Kd. And these are the applications, as I said, the types of assays that can be performed with SPR. The kind of information you get out of an SPR experiment is a yes-no binding, specificity, kinetics, which tells you the strength of binding. You get values for your on-rate, off-rate, affinity constants, concentrations, thermodynamics. And a wide range of biomolecular interactions can be studied. You can study proteins, nucleic acids, lipids, carbohydrates, and so on. So now, let me quickly show you a typical chip that we use. So in this experiment, we have used this chip. It is a CM5 chip, and this is the plastic case. I just wanted to show you the gold film. So this is the plastic cover, and you can actually see the surface where the interactions take place. So this is the middle one is the gold surface. So, and then we typically, this is a sample reagent rack where we so these are some of the vials where we can place our ligands, our analytes, our buffers, and then you close the rack and put it in the sample compartment rack. So we won't actually be able to show you how this is done because we have an experiment running, but you must have seen this in your Interactomics course, how the experiment is carried out. So now let's go straight to the data analysis part. So what I will be doing is going back and forth between a PowerPoint presentation and the actual VR evaluation software, so that those of you who are joining us for hands-on can follow us and do the steps as I'm doing it. And for those of you who are listening, can just watch the PowerPoint presentation. Okay, so the experiment that has already been performed is the ligand that has been immobilized on the chip is an anti-beta-2 microglobulin antibody. This has been immobilized on a CM5 sensor chip, which I have just shown you. And a multi-cycle kinetic analysis has been performed. the analyte concentrations, the analyte that was used was beta-2 microglobulin protein in increasing concentrations of 0, 2 nanomolar, 4 nanomolar, 8 nanomolar, 16 nanomolar, and 32 nanomolar. And we typically choose one concentration in duplicates. So in this case, the 8 nanomolar concentration was run in duplicates. The evaluation will be done, so the kinetic analysis of this binding will be done on the Biochemical T200 evaluation software version 1.0, which has been already shared with those of you joining us for the hands-on. Okay, so the first thing you do is open your software. Open the Biochemical T200 evaluation software. I'm working off the version 3.1, which is a paid one that we have in the lab, but it is very similar to the 1.0 which was shared with you. So when you open the software, what you do is you click on the file. You click on file and you open the file which says the data file, kinetics assay MOOC live demo. So this has also been shared with you. Okay. What you will see is when you go to when you open the file, you will actually see a blank screen. On the left side, there is a click on sensorgrams, and under sensorgrams, all sensorgrams. And you will see the output as shown in the window above here. Here, the green represents startup cycles, which is nothing but buffer that is flown over the, which is flowing over the sensor chip. This is to stabilize the system. You want to get it to a baseline level. And the red lines, they represent the sample cycles, the 0 as well as the increasing analyte concentrations. Then what you do is you click on kinetics. On the top tab here, you will find kinetics affinity. You click on that, and then you click on surface bound on the top tab. Ask yourself, why are you selecting surface bound and not affinity in solution? What would happen if you click affinity? Remember, this is a ligand that has been immobilized on a surface. So it is a surface bound interaction that we are studying. Okay. Okay, once you click on surface bound, what will happen is, this is the window that will open. Okay, what you see here, you'll find various information given here. So here, under curve, you will see flow cell is 2 minus 1. 2 minus 1 means that the sample is reference subtracted. Now, this is very important. When you're doing an SPR assay, it is very important to use 2 flow cells. In one of the flow cells will be considered a reference flow cell. The second one, flow cell number 2, will be the one where you immobilize your ligand. And the reason for this is, you remember that all the measurements here are based on change in refractive index. If there is, if anything apart from the ligand binds, if there is something in your buffer, if something binds non-specifically to your surface, you need to know that the change in refractive indexes, the measurements that you're getting, the RU units that you're getting are due to your ligand alone and not due to any kind of non-specific binding. So when you flow your sample over a reference surface and then over a sample surface, you subtract the sample from the reference. So that is what it means by FC 2 minus 1. It is reference subtracted. So you know that you have already subtracted any kind of non-specific binding to your surface. Then the next tab shows you the identity of the ligand. In this case, we have used anti-beta-2 microglobulin antibody. The sample, which is the analyte, is the beta-2 microglobulin protein. And the temperature is at which the reaction was run at was 25 degrees centigrade. Now, in this machine, reactions can be set to run between 4 degrees to 40 degrees. So depending on what are the best binding conditions for your particular assay, you can choose the temperature. Now you can explore in this window details such as cycle number, concentration of the analyte in nanomolar, the flow rates, contact time of your analyte with the ligand, and the dissociation time. And all these things are optimized during the setting up of your experiment itself. For example, the contact time is empirically determined during optimization of your experiment. So in this evaluation software, these are all things that were done in your experiment, and you just see the identity of each of these parameters. Now we are going to run the evaluation in a single mode. What happens in a single mode is you can deselect any of these curves. You can deselect any of these conditions to choose whatever best fits your, whatever you want to study. If you do in a batch mode, then everything will be selected. Now you click on next. Now the next screen shows you blank subtracted sensograms, and what this means is, you remember you had zero concentration in your samples. So in here it is subtracting all the responses from the blank. All the responses that you're getting in these different concentrations are being the blank is the zero concentration being subtracted from each of these concentrations. So ask yourself, what is blank subtraction? Why is it important, and how is it different from reference subtraction? In SPR, it is in this case what we are doing is something called as double referencing. So when you do reference subtraction as well as blank subtraction, you are making sure that the signal that you obtain is very specific to your ligand, and this is why double referencing is extremely important in your SPR assays. Now, next is you click on kinetics. Once you click on kinetics, this is the screen you will get. Here, you will now try to fit this, mathematically fit it to a, you choose a 1:1 binding model. Okay, and then you click on fit. Once you do that, this is the output you will see. It will go through many iterations and try to fit to each of these curves. In this view, I would like you to explore what are the different fits that are available apart from a 1:1 binding. Okay, and think, so for example, if you have a two-state binding, you might have a heterogeneous ligand, heterogeneous analyte. Now, what we suggest is you always start with a 1:1 binding. If you don't get a good fit, go back to your experiment and try to optimize conditions. If you know from literature already that it is a different kind of fit apart from a 1:1, it is not a 1:1, it is a different kind of fit, then go ahead, fit it to that model. But if you're starting from scratch, if you have no information about your system, start from a 1:1 binding model. Try to optimize a lot of your conditions beforehand. Make sure your experiment is done very cleanly, your buffers are optimized, there is no interference from any other compound, any other contaminant. And hopefully it will, give you a good fit. Okay, and then once this is over, this is the output you will get. So these are the result views. You will have 4 different views here. So as you can see, the first one is a quality control view. The second is a report, then residuals and parameters. So the quality control view will tell you whether all the quality control checks have been passed. So whether the kinetic constants are within the instrument specs, if the kinetic constants are uniquely determined, there are no significant bulk contributions, etc. So I would like you all to explore each of these 4 views, and then there are some questions on the next page. So those of you who have registered for the hands-on demo will have to submit the answers to these questions by tomorrow, tomorrow night, Sunday that is. And the top 2 or 3 will get a chance to come and uh, be shown the live demo. You can have some hands-on experience on our Biocore instrument here at IIT Bombay. Now what I will do is go to the actual Biocore evaluation and go through these steps again so that you can see how it is done in real time. Okay, so now I'm working of the Biocore T200 evaluation software 3.1. So I've opened the application. I'm going to open the file now. All right. So you come across this blank screen. On the left side, under sensorgram, click on all sensorgrams. This is what you see. So as stated before, the green lines represent the startup cycles. We typically run 4 to 5 startup cycles, which are nothing but buffer to stabilize the system. And the red lines are the samples. So now I'm going to click on kinetics, surface bound. All right. I'm going to run the evaluation in single mode so that right now I'm not going to deselect anything, but if I wanted to, I could deselect, say, one of the zeros if I didn't want it. And you can see as you deselect, the lines will disappear. Those curves, those particular curves will disappear. Let's say I want to deselect the 2 nanomolar concentration, which is the red line. If I deselect it, it disappears. So basically, in single mode, you can select what curves you want to analyze. Okay, nothing changes here. I want to do the 2 minus 1. All this remains the same. And then I click on next. So now the next screen I get is our blank subtracted sensograms. It has already subtracted the 0 concentration. Now in this screen, one thing you can do is, let's say you have some spikes in your data, something that will interfere with calculating your on rates, off rates, etc. You can remove the spikes in this particular view. So let's say I want to remove this. This actually does not interfere, but let me just demonstrate how you remove something. So you right click and then just drag. And then here you say remove selection. It removes it. Sometimes you get some spikes, in the middle of your data, and you might want to remove them. So you can again right click and say remove, and it removes it. But right now I don't want to, so I'm going to just keep the data as is. Okay. Next, we want the kinetics. So I'm going to click on kinetics. I'm going to fit it to a 1-to-1 binding. One more thing I want you to explore is the parameters. We'll talk a little bit about it later. So now we are going to
so what you'll say, like there's some technical glitch in that, so you repeat it. So Come. Yeah. Play again. Okay. From starting information from their sensogram. Yeah, from here. From here.
All right. I think there were some technical glitches, so I don't know how much any of you heard. Okay, so I'll start again with the analysis. So we have opened our data file and we will now continue with the kinetics. So click on kinetics, surface bound. Okay, so this is the screen you see. We are going to run the evaluation in single mode. Okay, please bear with us.
This is still not visible actually somehow. Can you minimize this one? But this screen is not visible there.
All right, please bear with us. We're still trying to resolve some technical glitches.
Okay. And you will explain it slide after that. Somehow what happens is that in this slide which is from there, this is not visible.
Okay,
So click again, do it again. From here you go.
okay, I'm going to start again and see. I believe the overlaid slide cannot be seen in the.
Live video. Slides. Keep it present. Wait. Screen not. So for this one, click on it. You go to this one. This one. This one. And again, this not coming out. So everything you can do this extension, you can put it in, you can set it, you can explain it also.
All right, I think we are not able to display the overlaid slide in real time, but it is actually the same as in the PPT. So it's actually quite self-explanatory, the PowerPoint. Right. So I was actually working off this particular window, and where I was showing you, you can remove your uh, spikes, extra spikes, is in this window. So when you get your blank subtracted sensograms, you can right click and select whatever selection you want to subtract, and then you click here saying remove selection. And this is very important if you have a lot of spikes in your data and you want to remove it from your analysis. It will interfere with your calculations. And the rest are pretty much what you will see, uh, what I was planning to show in the live demo. So once you come to this screen, you say fit to a one-to-one binding model. This is what you get finally. It will go through some iterations, just wait, and then you can abort this in the middle by clicking on the abort button, or you accept. You don't have to do anything to accept. It will just go till the end. And this is the final view. So in your final view, if you click on the report, you unfortunately I can't show it to you right now. In the report, you will have the calculated K-on constants, the association rate constants, the dissociation rate constants, your affinity constants, something called Rmax, which I have not covered in this session. Basically, Rmax is the maximum binding capacity of your chip at saturation. Okay, so that this is Rmax value is very important, especially when you're doing kinetics experiments, to determine how much of your ligand you want to immobilize on your chip. Uh, when you're doing a plain binding yes/no experiment versus a kinetics experiment, uh, in a binding experiment, you can allow as much ligand to be bound to your chip as possible. You don't care about, you just want to know whether there is any binding at all. In a kinetics experiment, you do not want it to go to saturation. So you have to be very careful how much ligand you are immobilizing on your chip. So we use the Rmax values to basically we want a maximum Rmax of 100 to 200 RUs, and we calculate that depending. There is a formula. You calculate that depending on the molecular weight of your ligand and your analyte, as well as the stoichiometric ratio between the two. So you have a theoretical Rmax, which is always higher than the experimental Rmax. What you get in your report is the experimental Rmax value. And you'll have a chi-square value, a U value, which tells you whether your data is statistically significant. You will have your residuals. There is there are limits beyond which, if you see your residuals, then you have to reject that data. You cannot take that. There are two red lines. So if you click on residuals, you will see that. For this kind of clean data, you will probably not see that, but in sometimes you do see them going beyond, and then you just have to go back and either remove the selection where you see those spikes, or you go back to your experiment and try to optimize your experiment to get cleaner data. So please do explore all these views, and then you can answer some of these questions. So we would like you to submit the answers to what is the value of the association rate constant that you see, what is the value of the off rate constant, what is the value of the affinity constant, is it high or low? In the biological context, how would you explain your answer? If you see high, why is it high? If it is low, why is it low? Is the fit good or bad, and how will you find out? And if you click on the parameters tab, you will see that the Rmax value is fitted globally. So if you change it to a local fit, what will be the change in all these values? So we hope you can submit your answers by tomorrow, and then we look forward to receiving your answers. And we hope you have learned something from this very short live data analysis session. And we hope that you will be interested to do some SPR in your own experiments. Uh, and please do contact us at IIT Bombay in case you want to do any SPR or want to learn some more on SPR. Thank you very much.